Good evening, everybody. My name is Mike Underhill, and it's my pleasure tonight to introduce the speaker and his topic of bright spark. So you will see at the moment, hopefully, the next two talks which are coming up. If my screen share is working, you should be able to see them. And the next two talks, which actually I will just have to move things, which I have done. The first one is on Tuesday the 19th, which is only a week's time, which is Digital Delivery of Projects in the Water Sector by Neil Cuthbert. And then on the 2nd of February, so we've got some fairly close together this month, or this part of the year, we have got Game Software Engineering. And welcome to our world by Witawat Charan, and he's a game developer at Creative Assembly. There are other talks further on down. So that is the future. But let me first of all mention one or two points, and then I'll introduce the speaker. And first of all, please only use the Q&A session. Don't use the raise hand or chat section. That will not be responded to. And we will actually put your questions into the Q&A sessions, and they will be answered. I will have a look through them and select some, or all of them if there's enough time, to ask the speaker to be able to continue on. So, so chat and hand raising will not in general be used. Anyway, let me introduce the speaker, and Malcolm Stevens. And Malcolm graduated from the University of Surrey in 1994 with a master's degree in electrical and electronic engineering. And he has since then had 25 years of experience in radar development, particularly specializing in synthetic aperture radar, the image formation of that, the post-processing, exploitation of it for a variety of radars from various production systems, and the production systems such as Searchwater, iMaster, and also to what is a technology demonstrator, which is BrightSpark, and some others on that, but he'll explain that. His work has also included signal processing and algorithm development for both monostatic and multistatic radar, performance prediction, trials planning, and acceptance. So a worthy 25 years. So I will now stop sharing my thing, if I can just get everything out of in the right places, and I will stop my own screen sharing, and I will ask you, Malcolm, to sign on and put your screen up.
Okay, hopefully everyone can see that.
Yes, so the floor is yours. Away you go.
Okay, I'm Malcolm Stevens. The title of the talk today is BrightSpark, which was actually the name of a project to make a technology demonstrator, a radar system that was developed a number of years ago now. And one of the challenges we were given at the time was to demonstrate the art of the possible in radar imaging. It's a nice quote, but there were also some numbers to back this up, and we were given specifications of performance or resolution to achieve. But before launching into BrightSpark, I've got a little bit of background on synthetic aperture radar as well. What it is, why we need it, and a little bit about the imagery and some of the things that you can see, before then talking about the development of BrightSpark, the flight trials that were conducted, and the imagery and post-processing that we've done on this, or at least some of the post-processing that we've done. And then a finally a small conclusion on where to go next. What are the next steps for radar imagery? So first off, synthetic aperture radar. Radar is traditionally known as something that's able to detect targets. So like in an air traffic control radar, where you're actually transmitting a pulse and waiting for the echo and detecting the range and bearing to a target. It's the other use that is commonly known is for police radar guns, where you're measuring the speed of a target. But in this case, we're using radar instead of optical frequencies to actually collect imagery. And in order to do this, we have to use a synthetic aperture. And I'll explain more about what that means and why it's necessary a little bit later. So first off, radar. Why do we need it? Why not just use an optical sensor? Full motion video, wide area motion imagery, there's a number of modern sensors that are all very capable. And the first answer is obscuration. The image here shows the amount of cloud fraction, that is how much of the month was obscured by cloud across the globe. And this was taken from March of last year. If you live in parts of North Africa or Australia, you've got a fairly good chance that you can actually use an optical system without obscuration from cloud cover. But you've also, even in these areas, you may have dust or sand or other things that mean that you can't actually see through that. So radar, the frequencies that are used allow you to actually look through most of the obscuration. Cloud cover and rain cause a small loss to radar, but they allow you to still look through it. There are frequencies that are used for radar that also allow you to even look through foliage, so tree canopies, and even down into ground penetrating radars. But in this case, bright spark is at a relatively high frequency for radar, and so those aren't really relevant in this case. The other reason for not relying on optical sensors only is that the illumination varies. If you look at different times of the day, you'll see color temperature change, the shadows will change. At night, obviously, you lose your main light source, and so therefore have to either rely on infrared. So when you actually come to do post-processing and to try and do some of the techniques like change detection, having an illumination source that is continuously changing makes it harder to actually do some of these post-processing techniques. Whereas radar, because it's an active sensor, it's effectively shining the searchlight, it's able to give you the same image whatever time of day or night. So that explains why we need radar. But why synthetic aperture? If you have a physical antenna, an antenna that is small enough and light enough that it can actually be put on an aircraft or a satellite and still allow the aircraft to take off and give you good performance for endurance so that you're not using all your fuel just to carry this big antenna around, you're limited to what beam width you can actually achieve. The beam width is inversely proportional to the size of the antenna. And so therefore, to get a narrow beam width, so you get high resolution in the imagery, you need a very big antenna. If we just put some numbers in the equation there, and if you have approximately 1 centimeter for the wavelength lambda and a very large antenna for the frequency that we're working at of a meter, then you get down to about half a degree of resolution in azimuth, which even at a very modest 10 kilometers away means that you've got something like 100 meters of resolution. And 100 meters of resolution, you can have a lot of objects within that. It's not particularly that high a resolution. And so therefore, you actually need to generate a lot bigger antenna. And these antennas are too large to actually be flown or put on satellites. The lengths can be measured in kilometers. For a number of the images that will be shown later, we've got apertures that have to be well over a kilometer long. And so therefore you can't make this antenna by physically carrying something and sort of that is that size. And so you use a smaller antenna and you transmit a pulse at one location, move the antenna, and then transmit at the next location, so that you're essentially filling in and making up a synthetic aperture using your own physical antenna, and just then putting all the data together in post-processing sort of to actually form the image. I won't go into any of the details of exactly how you do the image formation, but a few things are pretty useful to help understand the radar imagery, and I'll cover some of those a little bit later. So first off, comparison, the obvious difference, we have color in the optical image, but if we take that away, then you're left with something which actually can look reasonably similar to a SAR image. A number of the main features are clearly evident in both. You can see all the field boundaries, you can see where buildings are, you can see where the roads are, the gantry over the railway in this example, and you get some features that actually stand out more easily in the optical image, but others stand out more easily in the SAR image. So things like the rails actually reflect more and have more contrast than in the SAR image than in the optical. You also get differences. The bright coloured roofs of the buildings on the top left of the image, so sort of around here, they're bright in the optical image because they're light coloured, but to the radar they're dark, but you see a strong reflection off the wall. And this all comes down to one of the fundamental differences between working with radar frequencies and working with optical frequencies. The wavelength. If we look with optical light, we've got wavelengths which are in the range from 400 to 700 nanometers, so they're incredibly small. And therefore, almost every surface that you look at with visible light appears rough. And so you get diffuse scattering that scatters the light in all directions, which allows us to see an object whichever direction it's lit from or we're looking from. But when we go to radar frequencies, and I've listed a few of the frequency bands here that are traditionally used for long-range sensors, for L-band, through to some of the airborne surveillance radars up at X-band, and finally we're working up in the higher Ka band. So the wavelengths there are changing from 30 centimeters instead of nanometers, or hundreds of nanometers, to, for Ka band, we're just under 1 centimeter. But at X band, which is traditionally where a lot of the long-range surveillance radars have been, it's 3 centimeters. And so many surfaces still actually appear to be relatively smooth. Not quite mirror flat, but certainly smooth. And these surfaces are things like tarmac and concrete, and building materials, brick and wood, tend to actually look pretty smooth to a radar at X band. And so when we move up in frequency to Ka band, which is where bright spark is, then we actually start seeing surfaces get a little bit rougher. And so we actually start getting a little bit more diffuse reflections. So we start seeing a few more details that weren't necessarily apparent in the traditional radar bands. But in general, you get a lot of the light hits surfaces and reflects away from the radar, and relatively a small amount of that actually reflects back to the radar. So you obviously need sensitive sensors in order to be able to detect that small amount of reflection that's coming back. But SAR is an active sensor, it's illuminating the scene. And so therefore you get the same things as you would in normal physical optics. You get shadows behind the object, you get specular reflections when you look straight at a reflection straight from the broad side of a wall or something that is physically large. The shadows are seen behind the object. So in this example, we've got a pylon, easily recognized, with the shadows behind it, so they're further in range. But the other thing to note here is that the top of the object is actually closer to the radar than the base. And radar works by transmitting a pulse and measuring the time it takes for the echo to come back. And so we're actually measuring the distance to the object, not looking at it in the same way as a normal camera with a lens. And so by measuring the distance, we actually see the top of an object appear closer to the radar than the base, and you get this effect called layover. If you're looking at something which isn't just a tall vertical object, you get a similar effect for a hillside, for instance, where the top of the hill will foreshorten and squash the side of the hillside that's rising and stretch the side that's actually falling away behind it if it isn't shadowed. Measuring the other angle, though, you can measure downrange distance fairly easy with a radar, but actually measuring the cross-range position and forming that image takes a little bit more processing, and that's where the synthetic aperture comes in. So if we now move on to Bright Spark itself and the radar, the challenge was to build an ultra-high resolution, 5 centimeter resolution radar. So requires a fairly wide bandwidth, over 3 gigahertz of bandwidth, operating at Ka band, which is up sort of around 30 gigahertz. The starting point for this was a production system, an iMaster radar. I'll explain a little bit about what we could keep and what we had to actually replace. But we also had to then develop the processing to take us beyond the resolutions that we'd got with the production system. We then followed that with a fairly intensive set of flight trials. The actual development was spread over 12 months, and the starting point was a Ku band, so a different frequency band radar, which had both synthetic aperture radar and also ground moving target indication. The two are complementary parts to radar. One looks at the still stationary objects, the SAR. The other one detects the moving targets, the GMTI. For this demonstration, we were only concentrating just on the synthetic aperture imagery. Because the components that are used are all sensitive to the frequency, even something as simple as the radome, a fiberglass or laminate material is transparent for the Ku band radar, but it appears lossy and opaque when you try and look through it with Ka band. So you've got to even replace things like the radome, but the transmitter, the antenna, all of the up conversions and down conversions, we generate the signals at a lower frequency and then up convert them to the frequency that we transmit. And so all of that has to be replaced. And because this was a technology demonstrator, we didn't actually have the time to design and package all of these components as you would do a production system. And so what we actually see in the photo at the bottom is that the section which is grey as a strip around the middle is actually where we housed some of these new components. And we were able to buy off the shelf connectorized components to save time and save effort in design. The end result was something which keeps a large part of the form factor. It can still fit in exactly the same size, so on the same aircraft that we'd previously fitted the production system. And the challenge we were given, as well as the demonstrating the art of the possible, was this 5 centimeter resolution imagery. At the time, to my knowledge, there were no other Ka band radars that were achieving that resolution, although others had got, at X band, there had been one demonstration prior to producing this radar. The flight trials, typical of any flight trial that I've worked on, was spent in the middle of winter when it's freezing cold, and actually was split between 2 months for the initial trials, not intentionally, but we got snowed off and so had to retreat, go back, and then go sort of attempt a second flight trial when we could actually get back in the air and it was safe to use the airport and the airport was open again. We deliberately went out and collected a wide variety of scenes, trying to get things that would be interesting to look at, but also challenging to the processing, so that it will allow us to develop the processing and make it robust. The following year, we were actually, having produced some successful images, we were then contracted to then continue these and collect a large amount of data within a very short space of time. In just a week, we collected over 180 data sets covering 24 locations spread around the UK, and formed over 2,200 SAR images just from those trials. But in total, we formed something like 3,000 images from the Bright Spark radar over the first 2 lots of trials. We had a variety of weather conditions. We had winds that meant that when we were flying a racetrack where you fly one direction to collect one image and then turn around, fly back the opposite direction, we had speeds that were 3 times faster with the tailwind than when we were actually returning. So changing between 60 knots and 180 knots, meaning that it was a good challenge for how robust the radar processing was. The examples here just show a few of the images and actually show the aircraft we used to collect the data. But I'll explain a lot more about the imageries throughout the rest of the talk. So the first reason, this 5 centimeters, if we look at radars that were commercially available, things like satellite radars achieve sub-meter resolution relatively easily. Now there are some that are down sort of around 30 centimeter in one axis that are commercially available, like Terrasar. But at 40 centimeter, if we look at an image like this, it's quite challenging to actually see what it is. If we start to improve the resolution and go towards 5 centimeters, we start to get a better idea of what the objects are. In this case, we've got 2 cars which are parked near some grass. Context obviously would help you to identify them, but the main aim here is to try and achieve that high resolution. But as well as seeing high resolution, you can also see other effects. Because we're working with about a centimeter wavelength, we're able to see effects such as frost and snow. The frost isn't readily apparent in the first image compared with the normal image, so I'll show on the next slide a comparison of that. But there's a fairly obvious difference when you're seeing the snow that actually reflects from all of the taxiways and dispersals on this airfield. And so you actually are seeing a stronger reflection of backscatter because the surface is now rougher because it's covered in snow. When we actually look at the detail of the aircraft, normally if you've got a smooth surface, all of the energy, or the vast majority of it, is reflected away from the radar as forward scatter, and very little of it actually gets reflected back to the radar. And so that's what you normally expect to see on the smooth surface of the upper surface of the wings and the fuselage, because obviously it's got to be aerodynamic for an aircraft. But when it was frosty, we get water droplets that are frozen, and in this case we've got a lot rougher surface. This image here has used another technique of post-processing to combine images that were collected from different directions and assign each one a different color. So if all of the images add up and have the same reflection in all of them, you get a grey color. But if it's only present or stronger in one or some of the images, then you start getting color casts. So in this case, you can actually see a color cast from the shadows that are behind each of the aircraft. And these are appearing as these sort of rainbow of colors because of the colors we've chosen. But the wings here, instead of being this non-reflective surface that you see in the normal image, we're now getting a rough surface and therefore getting reflection. And that's partly due to moving up in frequency to Ka band and 1 centimeter wavelength. We can also use the shadows to provide additional information. In this example here, 3 aircraft on a grass taxiway, and you can see quite quickly which has got the single tail fin or the twin tail fins. you can see the engines on the wings quite quickly. But you can also use the shape of the shadow to tell you information about the geometry of the aircraft. In this case, we're fortunate enough to get a specular reflection off the front of the wing. So we can see that actually it's got flat wings, not swept wings as the shadow possibly looks. And so that then tells us that the wings change height, so that the wings are low at the base of the fuselage and then increase in height towards the edge, whereas the one on the left actually has flat wings. So you can actually gain more information just from looking at the shadow without looking at the bright reflections. And in fact, the image on the right is of the same aircraft viewed from 90 degrees away from that. And so that confirms that the wings are actually straight on these two aircraft, or in fact all of the aircraft. But the shadow always appears exactly behind where the object was during the collection of the radar data. But the reflection, because the radar is measuring distance to the object for the downrange axis, in the other axis it's actually measuring how that distance changes. And so it's looking at effectively at the Doppler frequency. And if you've got a target that's moving, the motion of that target actually displaces where it appears. So on the left here, we've got a slow moving bulldozer that's actually flattening the ground here. But you can see that the shadow has moved barely at all, but it's obviously changed speed, which has meant that the bright reflection from this object actually is displacing away from where it would normally be. The shadows depend on the geometry that you've collected the image though. If you fly higher and look down more steeply, you'll shorten the shadow. If you fly lower, you'll lengthen the shadow. Same as when you're illuminating with daylight. In the middle of the day, the shadows are shorter because the sun is higher at those times, which can make it challenging to actually recognize just from the shadow. But because we know the geometry we've collected these from, we can actually correct for that and make it look as though the shadow has the same geometry as the object that caused it. So in this case, it becomes a lot simpler to actually recognize that these actually are the same vehicle. But we can also use the fact that we get reflections off many surfaces, so walls and the ground all act with most of the energy being reflected rather than away from the radar rather than back, actually means that we can potentially see both sides of a vehicle in the same image. So at the top of this image here, you've got vehicles that are seen directly, so the direct path to the vehicle, but also you've got a second image, which is just below, which has been reflected off the wall, and so is actually at longer range. And in this case, it can be easier to recognize the shape of the vehicle from the multipath than it is from using the original direct path signal. But it means that you're able to gain more information about the objects that you're looking at in the scene. We also see other effects. The image I showed earlier with the pylon actually has shadow behind the pylon, but these lines here aren't actually shadows, they're diffraction. So it's similar to the 3-slot experiment that you might have done in physics, where you actually put 3 gaps and shine a coherent light through it. You set up a diffraction pattern behind it. In this case, we haven't got 3 slots. We've actually got 3 obscurations. But the equivalent is equivalent to doing 1 minus the other case. And so therefore, we actually still get the diffraction pattern that's seen behind these collection of wires. And we can confirm that it actually is diffraction because we also collected imagery of the same area with the iMaster radar at KU band. And so we can actually see that the width of these diffraction pattern here actually changes with the images that are collected at a different frequency. And so we can confirm that this is diffraction that we're seeing, not just a shadow. We also get other effects that appear in physical optics. Normally, when you look with a normal optical sensor, you would expect to see wires like telegraph or power lines from any direction you're looking at them. And that's because the optical wavelengths are so small that you get this diffuse scattering. And so with a radar, we would normally only expect to see a strong reflection when we look side on to the wire. So when we're getting a specular reflection back. But in this case, what we see is one side here, we get no reflection from the wire. And on the other side, we do see a reflection, but it's not at right angles to the shadow. And this is actually sort of because of a phenomena called Bragg scattering. If we actually change the direction that we collect the image so that we're now looking orthogonally to the wires, we see that we get a reflection of both wires. So there really are wires there. But what's happening is that we're actually looking at the spacing of the different strands of the wire. And when that spacing is viewed at half a wavelength, so that the path to it and then the second half is when it's coming back, add up in phase. And so therefore you actually get a stronger reflection than you might expect from this Bragg scattering. So this is actually the same phenomena that causes butterfly wings to scintillate in light. But with bright spark, because we've gone to finer resolution, we've gone to 5 centimeter resolution, it means that we're actually collecting our synthetic aperture over a lot wider angle than we actually are seeing this bright flash. And so by taking the wires and making them horizontal in the image here, and then taking the spectrum of those, you go back to the equivalent of looking at the original pulses. And so we can see that most of the time we weren't getting a reflection. But for this short period, we get a reasonably strong reflection, and then it's back to seeing almost nothing again. So we're working at resolutions that are beyond the limit of what we can actually focus up, which basically in real terms means that this particular scattering, we can't focus up and produce 5 centimeter resolution because it's not actually present for a long enough angle to actually focus and put all the data together. And so we're working beyond the limit of the scattering from some of these objects. We also have other effects that we see. In this example, collected in quite a windy day, but I think it would be quite unusual to have a mast that's above this building with a wire that actually is moving quite as much as the displacement here. And this is exactly for the same reason that the bulldozer displaced. Because we're measuring the distance and how it changes, we're measuring the Doppler frequency effectively, we're actually seeing this displace by a lot larger extent than the physical displacement. So it may only be a small vibration, but it's sufficient to actually make it look as if the wire is spreading over quite a lot larger distance. So there's a number of details that you can pull out by having such fine resolution. A lot of what I've shown so far, with a couple of exceptions, have been single look images. By single look, I mean one image that's collected from a single aperture. Because we've got a coherent sensor, we've got the same as you would get with a laser or a LiDAR system. You get everything that's within 1 pixel adds up coherently. And so therefore it gives this effect, this random effect that appears like noise, which is called speckle. And it means that in this case, the grass around this mast or sort of around this vehicle, which without staring at lots and lots of these images, you probably wouldn't recognize as a vehicle. The grass doesn't look quite the same as it would do in a normal optical system or just viewed with the naked eye. It actually looks a lot noisier. And that's because we haven't got the advantage of averaging multiple images or multiple sort of the energy from lots of photons of light actually hitting the sensor. we're coherently adding all of them up, and so they're all in phase or out of phase. But by collecting multiple images from different directions and putting them together, we can actually reduce that effect and get something that's more familiar and looks more like an optical sensor. So in this case, going between the images here, we're actually seeing a lot more detail. And so this now looks a lot more like the structure of the clumps of grass that you would see. The tracks that are in the grass, you're able to see a lot more clearly. You can even see trodden down parts within the grass here. But the strong reflections off the antenna all line up, and so you actually get a clearer view of the antenna as well. But you also collect the different reflections that were strong only in limited angles. And so the vehicle here goes from something which is possibly only recognizable by measuring the dimensions to something which now you can actually see reflections off the window line, the spare tire on the back, the roof, bonnet, the wheel arches, the wheels. But because of the layover effect, the fact that you're measuring the distance to the object, it appears to have fallen over rather than being upright. But using this multi-look technique can also be applied not just to improve the appearance where you are seeing the object the whole time. If we look in low frequency radars that are used for foliage penetration, the idea is to use a frequency that's low enough that it sees straight through the tree canopy, the leaves. With a frequency as high as bright spark, you can't see through the tree canopy. But if there are gaps in between the trees, you can potentially look through each of those gaps, and then by collecting multiple images again and putting them together, you look through a different gap, and so you actually build up a picture of the ground. So in a single look image, you see a lot of shadowing, and it can be at times challenging to work out, is this area here part of a tree or is it part of the ground? By collecting and putting all these images together, we're actually able to get fairly strong reflections from the tree canopy that's visible the whole time. But where we've swept the shadows across the ground, you actually then produce contrast and you can see the ground, but the levels that you get are lower. So it means that you can actually start pulling information out about things that are below the tree canopy as long as there are gaps. It obviously wouldn't work if there are a completely dense canopy that there are no gaps in between to actually look through. So if we go back to the benefits of the resolution and now take the example from before with a single look image and then combine them in exactly the same way as I've described for the multi-look images, we now go to something which is a lot more recognizable as vehicles, down to the point that you can actually see the wing mirrors on the side of the vehicle in the higher resolution images. And actually recognizing it as a car becomes fairly trivial now. We can also put this together for objects that are physically very tall. Because we're measuring this distance to the object and it's changing, we have to be careful that we collect so that the distance to the object doesn't actually change when we change the angle. So if we flew a circle around a tall object, the top of the object would actually move towards us in all directions, and so would actually produce a circle around the point at which it's located. But by flying a straight line, which is quite convenient because it's simple to do, and pointing the antenna initially forwards and then gradually following backwards as you fly past, you're able to actually get an image which has combined lots of multi-look image or lots of single look images into a multi-look image of an object, in this case about 60 meters tall. And you can see in this case we were looking through cloud as well, and so seeing the ground when the photo that was taken actually during the flight shows that an optical sensor wouldn't have seen the ground in this case. They would have just seen the tops of these wind turbines. But the other difference with bright spark compared with most of the radars, the conventional radar products, was that it moved up in frequency. And by moving up in frequency, we were also not just getting this finer resolution, we're also able to actually start seeing the surfaces as being rougher, such as tarmac and concrete. And so that means that when you then put a smooth surface like paint on that, you see a difference in the reflectivity. You see stronger reflections from the tarmac or the concrete than you do from the paint. That allows us to then see things like the painted markings, in this case on the car park. And so you're actually able to pull out details which wouldn't have been readily apparent if we were working at the more traditional radar frequencies. You can also see, in this case, the painted company logo on the grass here has obviously killed the grass on some of it and not on other parts, because you see that it's still healthy grass on parts, but it's smooth surface on others. So you can actually sort of gain more information by being up at these higher frequencies. Talked earlier about the fact that we want to do post-processing of these images. One of the obvious things to do is, if you're collecting an image of the same area more than once, you can actually look for changes in the scene. So you can do change detection. In this case, we've got an image that was collected before the changes took place. Relatively simple scene. You've got the mast that I showed earlier. One of the vehicles was also highlighted, and you've also got people that are standing in the middle there. And for the second image, there's some fairly obvious changes. And you can see those changes by using just false color, just by putting the first image as red and the second image as blue, which gives the aide-memoire of red is fled, blue is new, and allows you to actually detect the objects that have appeared in the scene or left the scene. And the ones that are grey or white are still present. But with the single lick imagery, you've still got to contend with the speckle, the fact that actually that the background is noisy. But by combining that with the multi-look, you're able to then start to look at these a little bit more clearly. The background becomes less noisy, and you actually then start to be able to see the detail of what's either arrived or left. But I mentioned earlier again that radar isn't just an amplitude. It actually is a coherent sensor, and so therefore we've got phase information as well. So instead of looking just at large scale changes of has the amplitude got brighter or darker, we can actually look, even if the amplitude is the same, has something disturbed the ground to cause a physical change that we can detect with the phase. So, for example, a vehicle track or other things. One of the examples that shows this quite clearly is we can see in this image, we'll actually deliberately put corner reflectors out, and we're instrumenting to measure the performance of the radar. But in the neighboring field, there were sheep. And we can actually see the shadows of the sheep. And because we're fairly fine resolution, we're able to actually see sort of down to almost the legs and the head of the sheep showing up. But you can see quite clearly in this change detection image where white shows that there is no change and black shows that there is potentially a change there. You can see that the tracks of these animals are relatively easy to spot. When we were designing the radar and putting it together, because it was a fairly rapid adaptation of an existing radar, we actually had a compromise that we had one clock harmonic. Normally you would design the RF, the radio frequencies, to deliberately avoid any harmonics of any of the frequencies that you're using within the system from being within the band that you're actually trying to look at. Because we were taking and adapting an existing system, we actually had a compromise with one clock harmonic present. And so what we see here is, in the previous image, we'd got shadows from tall objects. But what we see in the change detection for the first images that we processed was that these weren't shadows, they weren't random noise that appears in the shadows. They actually had a coherent source of information in them. And this was because of this one clock harmonic that was present in the system. When you do the image processing, it spreads that harmonic across the whole of the image. And so instead of seeing noise in the shadows, what we're actually seeing is this clock frequency. It's not really visible in the SAR imagery because it is down at the level of noise. But when you start putting hundreds of thousands of pulses together, it adds up, and it's just louder than the noise. But again, this was something that we could predict exactly what frequency this was, where it would appear in the image or in the processing of the data, and so we could actually correct it in the SAR processing, and so remove it in processing rather than design it out at the before actually putting the hardware together. And so the image on the right is from the exact identical data as this, but with a relatively simple stage added to clean up this one harmonic. So I commented previously about speckle in the images and the fact that this can be awkward to work with because it makes things noisier. For the amplitude information, we were able to average this out using multilook, and we can apply a similar technique to the change detection results, the coherent change detection results. So here we've got a building which is shown on the left and a vehicle on the right. And you've got grass all around the vehicle, and in this case you've got an area of grass in front of the building and then the roof of the building across here. By putting, again, multiple images together, you're actually able to get rid of a lot of that noise. You're now starting to see, first off, that you have got faint tracks that were present here. And what we know actually for this was that the vehicle didn't actually drive round in that arc before, after the first image was collected and before the second. It actually had driven round before either image was collected. And so what we're seeing is, rather than the strong change that you would normally get from a car driving over grass or mud, we're actually seeing a small amount of the spongy surface, because it's peaty grass, was actually just bouncing back slightly. And so it's actually a very subtle difference that we're now able to detect. And in the image on the left, we actually start by putting such high resolution together and putting enough images to get rid of the noise. We're able to see things like windows and doorways, and so we're seeing the physical structure of the house and getting change detection that not only looks at the grass in front of it, but actually at this point you actually have got multiple surfaces all on top of each other when you measure the range, because you're going across to the base of the wall, going up to the top of the wall, and then across the roof. So you've actually got three surfaces all on top of each other here, but you're still able to get change detection that you can actually look at for this. So if we go back to the earlier image of the sheep, we can see that by applying the same techniques here, we can actually get down to individual footprints from each of these animals by combining multiple images. So it gives us something which is incredibly sensitive to look for changes in a scene. But why stop at 5 centimeter? 5 centimeter was the challenge we had, but why stop there? Why not actually go for wider bandwidth or have longer apertures, deliberately just collect more data and process it coherently? So we've actually looked a little bit at that too. So this is a 5 centimeter resolution section of the image with the aircraft earlier. I showed these three highlighted earlier, but this one here, it's actually got I think probably riveted, or there's some structure which someone who's a lot more familiar with aircraft than I am would probably be able to recognize what aircraft it was. But by going to finer resolution, in this case 2.5 centimeter, we can clean up the image quite considerably. You can also see more detail from the vehicles that are actually parked below the wings, and so you can actually see some of the structure of these more clearly in this image than you could in the previous one. So why not actually go further than this? So what is the next challenge? Do we go for finer resolution? we're already approaching the wavelength. We're getting 2.5 centimeter imagery with a wavelength of just under 1 centimeter. And we're seeing the effects of things like Bragg scattering and resonance scattering that you would see even at the coarser resolutions, but we're now seeing those effects actually limit the resolution that we can achieve in some of the imagery. Can you go wider in bandwidth? One of the challenges here is actually regulatory. It's the legal requirement to have a transmit license. And although 5 centimeter resolution had been demonstrated at X-band, it couldn't be put into a production system because you couldn't get a transmit license for it. And the team over from Fraunhofer in Germany, who actually demonstrated this first, had to operate over a military range and figured they were only going to collect one image and no one would notice. Whereas the bandwidth is more readily available at the higher frequencies. Ka band makes it easier to get this. But if you carry on moving up in frequency, you start to then get more challenges with actually getting the power in these smaller components, because everything shrinks when you actually go to higher frequency in terms of waveguides and other components. You also get more absorption through moisture in the air and rain, and so the all-weather capability starts to diminish if you carry on getting higher and higher in frequency. Should we actually look at using multi-look more? From the examples that I've shown today, you can clearly see that it makes the radar imagery look more familiar by removing this speckle noise and making it look more like an optical image, although with obvious differences of the geometry that you've collected, the fact that you've measured the distance to the object and therefore have these layover effects that make things look as if they're falling over. You also, by doing the multi-look, you lose the shadowing, but there's nothing to say you can't retain the original images as well. Or should it just be more widespread use of SAR? It's a fairly capable system, and the post-processing, the examples I've shown here, just scratch the surface of what you can achieve. It's widely used from satellite observations for measuring everything from biomass to looking at glacial movement to monitoring earthquakes or volcano activity. You can measure height by collecting 2 images and using interferometry. There's an almost endless list of additional things that you can do with the data. The data that we collected has also been made available. GSTL, who paid for the development of the radar, have made some of the data available through a website. And this is available for research institutes and universities to actually experiment and try ideas out. And I just ought to, before concluding, just make some acknowledgements. Creation of the lecture obviously was supported by Thales UK. Although I had to write most of this in my own time, all of the imagery obviously came, and the tools that I was using and everything else came from Thales UK. And the radar itself was designed, built, and operated during the flight trials by Thales. But it was all funded by DSTL in the UK, and I've liberally used Google Earth to provide examples of optical imagery for comparison here. Now, if I throw it open to questions, hopefully Mike has been collecting the questions and filtering them through if there are too many. So I'll throw it open now.
Right. Thank you very much, Malcolm. Just let me check. Is my speech on with you?
Yes.
Good. Thank you very much. Right, and well done. Lovely talk. Yes, indeed, we've got some nice questions. But before going on to those, I've got a couple of things to which I should have said earlier. One of them that David James will be putting up. David, can you put it up now on the chat? I haven't seen it. Having said that we weren't going to use the chat so far, then we actually you want to use it just for this particular information. And so the information, I think Ian Simpson asked, what was CPD certification available? And the answer is certainly yes. And can we put it, David, I don't know if you can pop it up on the chat for everybody to look at it while we're doing it. The other thing which I should have said earlier was a bit of a useful advice on these things, that the view,
I think we might have lost Mike.
Yes. Hello, go ahead.
Okay, you're back.
Am I back?
Yep.
My internet connection has gone unstable again, so David may have to take over. But let me know. We'll go straight into the questions now, and thank you all very much for the questions. The first question was from Doug. Is if there is more than one radar being used, how does the setter identify a signal which is transmitted in the time it's transmitted? I think really the issue of the question is
You've gone again, Mike. In most cases, there is only one radar being flown at a time in a local vicinity. But if you are actually anticipating that there will be multiple radars, then you can actually put things onto the waveform to identify your signal as opposed to another radar. But typically, I mean, for this, which was a technology demonstrator, we were the only radar that was actually transmitting, and so therefore we didn't have to consider that.
Okay, thank you very much. Then the next was a comment. I'm sorry, John lost picture at one stage, but I hope we got them back. Then there was Jeff F. Was a question. Ka band suffers significantly from atmospheric attenuation. Was this a problem? And what sort of standoff range were the images recorded from approximately?
We've seen attenuation that can be relatively strong even at the lower frequencies for absolute torrential downpours. But in this case, we actually, for some of the cooperative targets, we had people on the ground on the radio saying that they were having to sweep an inch of standing water because it was raining so heavily. So we were operating in pretty torrential conditions at times. It does attenuate the signal, and it attenuates it more than at X band or KU band. But this was where actually collecting multiple images and being able to put them together was able to not only recover the speckle, but it also improves the signal to noise. So we may be only tens of kilometers for collecting these images, but we are able to actually still get respectable signal levels even in pretty inclement weather.
Okay. Can I just add a question of mine? What kind of transmit power levels are you using on that? Because that relates to the range limitation, does it not?
Because we were doing a technology demonstrator and we were having to design it quickly, we just bought an off-the-shelf transmitter, and so we were limited by what was available. And in fact, I think it actually came from a communications. It was designed for communications devices, so it's a fairly modest wattage. I can't honestly say what the power was off the top of my head.
Okay.
But tens of watts.
Okay, that's right. Shall we move on to a couple of questions from Mark? First of all, do you feel that RF systems are becoming optimized? In other words, have reached their limit, and future improvements will be in post-processing of the data to enhance the images. So is the RF system at its limit? Which is related to my own question.
When I started work 25 years ago on radar, one of the early tasks that I actually did almost as soon as I joined the company was to look at synthetic aperture radar. I was told at that point that it was a mature technology, there's nothing to learn, and we're not going to achieve much more. I think the differences in resolution that have been achieved have shown that there actually was plenty that could be done at the time. Whether there's quite the same sort of leaps that can be made forward is probably a little bit more challenging in the future. But certainly there are other things such as using polarimetry, using the polarization of the transmitted waveform, using multi-static systems where you actually have one transmitter and multiple receivers, or multiple transmitters and multiple receivers all working together, can actually add quite significantly to the ability to collect data and to characterize the scene quicker and more effectively. But yes, I think the post-processing, not just putting images together, but actually using, if you look at things like artificial intelligence, where Google and various other companies have thrown a huge number of millions or billions of images at these deep learning and machine learning techniques. These are all characterized based on optical images, but we can actually take advantage of that if we're producing radar images which start to approach the character by getting rid of the speckle. We can actually possibly improve the transfer learning that can be taken from these optical techniques across to radar.
Okay. Another question from Mark. The second question from Mark is multi-look radar, image radar, the separation set by the wavelength or by the resolution you desire. In other words, the separation between the look directions. Is it the wavelength or the resolution?
The multi-look, if you collect an aperture that is completely independent, you've got a totally independent image. But if you overlap the apertures, because you've got multiple things reflecting within each pixel, you actually do get some separate information. So you can actually overlap the apertures and produce images which share part of the aperture and still get independent phase, and therefore an independent speckle from those. And so you actually still can gain some advantage by overlapping the apertures.
Okay. Right, an anonymous attendee was, how well would the radar perform with ocean imagery? I think you started mentioning that towards the end, but would you like to make any further comments on that?
The SAR imagery that I've shown so far was all looking for relatively slow-moving or stationary objects. When you start looking at the sea surface, the waves and the wind can actually mean that you're looking at the whole of the surface is actually moving slightly. And the way to combat this is travel faster so that it becomes less significant. So it means that satellite SAR imagery can readily be used very easily to image large areas of the sea surface. There are satellites that their main task is to find shipping, and so therefore they look for these bright objects in amongst the sea clutter. But you can also use radar to detect surface surfactants. Oil spills and other spillages will actually affect the small-scale ripple of the wave structure, and so therefore you can see a difference from an oil spill or from a ship that's actually sort of disposing of things over the side of the boat. These can be seen in SAR imagery because they affect the reflections and the structure that you see coming back.
Right, thank you on that. Yeah, I'm sure that answers the question. I've just received a message, further message about the CPD link being sent again. David, can you manage to do that while we're continuing to answer the question?
Yes, I had already posted it on the chat. I'll put it up there again.
cropping optimization, in other words, non-military things, growth, delta, weather attrition, etc. And my internet's just going unstable.
Costs can be quite high if you are buying a single system, but if you actually look at some of the commercial satellites, then their business model is put a lot of money into actually getting the sensor up there. Once it's there, it stays in orbit and collects over a relatively long period. And so therefore, for commercial use, the satellite operation can actually be a useful way of collecting imagery over wide areas, and certainly it has been used to look at deforestation or to look at measuring the amount of biomass, so looking for the volume of mass of trees and foliage and sort of agriculture, looking at which crops are growing and when they're harvested, so you can look at yield. You can use the statistics of the image of a crop to actually characterize what type of crop is growing there and reduce the amount of surveying that has to take place by going and physically inspecting. And so this can be used for looking at crop yields. It can be used for quite a number of other reasons. I think going out and buying a very fine resolution radar such as this may not be a sort of thing which is necessarily obvious for commercial use, but I think there are probably certain industries that would actually find it quite useful. If you've got things like oil pipelines that you want to protect, then actually having something that can regularly fly up and down the route of your oil pipeline and look for, has anyone driven up to it and started siphoning off oil, it would actually save that kind of industry quite a lot of money compared with having to send people out to inspect them.
Okay. Right. We've actually got a lot of further questions coming in, so we may have to ask you to give fairly brief answers to some of them. And perhaps one question from John Harris is, how many frames are you capturing to do the multi-view?
We were typically collecting over about a 90-degree angle. So we were squinting forwards up to 45 degrees and then flying past and looking backwards. So squinting backwards by 45 degrees, which means that we were getting sort of typically minimum of sort of 8 images, most probably 16 or so images that we were putting together. You get, because you're putting together images and looking at the noise, each time you double the number of images, you get the same effect. So going from 1 to 2, you reduce the noise by an amount. Going to 2 to 4, you get the same effect.
Okay, moving on. How do you deal with motion blur when you've had so much variation in bad weather?
The motion blur that you get from wind-blown clutter, if you put the multi-look image together, the motion blur is always in the Doppler axis, the cross range. And so therefore, as you swing that round through 90 degrees, you actually swing round the direction that's being blurred. And therefore you actually suppress some of that motion blur by combining the multi-look. We did some trials which we were deliberately going out to try and collect imagery with nothing stationary, so trying to image just woodland. And we got the stillest day you could ever imagine. On other days, though, we had, as I said, sort of 60-knot winds that were blowing the aircraft and similar kind of levels of wind on the ground. So multi-look's one technique that can actually help you there.
Okay. What time, sorry, that question was from Benjamin Smith, and then from Andrew Morby, what time frame is the processing from capture to final pictures? How long does it take to process?
At the time we put this technology demonstrator together, we'd got, didn't want to be limited by the processing that you could actually fit real time in the system. And so therefore we made this as a data gatherer. So we actually gathered all the data, brought it back to our office, and then processed it up afterwards. But realistically, you can collect and process the imagery within seconds. So it may take you to fly your kilometer will take almost as long as it actually then takes to actually put the image together.
Right. Next question. Any advantage with working with at two close frequencies simultaneously to enhance the images, some sort of spread spectrum, in other words?
There are probably things that you can do by using completely different frequency bands. But the wider the range of frequencies you use, the more you can learn about the materials you're looking at. So by using two closely spaced frequencies, why not just extend and actually use both of them to get fine resolution? Or you can actually try and characterize in frequency to look at what reflects at one frequency but not at another. So you can actually look for absorption from certain materials. There are papers published showing that that can be done for geological surveys.
Okay. What next comment and question from Gavin Watkins. Hi, great talk. How accurate does your flight position data need to be?
The accuracy of the navigation sensor will determine geolocation more than it determines the image quality. There are techniques that can be used that mean that you can get away with a relatively crude sensor. We've actually got a fairly high quality navigation sensor on board, but to actually form the images, you don't rely on that. But to geolocate them and position them on the ground, that's where you're reliant on the accuracy of your navigation sensor.
So it's all done in the post-processing software, and it's sort of auto-focusing and all those kind of things, presumably.
Yes. Yes, okay. Similar to a camera, it's got an autofocus, but in this case, it's based on the data rather than something that's done at the time you're collecting the data.
Right. Anonymous attendee, could you explain more about shadows and how do you get a reflection from something that is not physical? Maybe you'll have to try and give a brief answer to that, Malcolm.
Both an optical system and a radar are both using electromagnetic waves. So it's both using a light source. It's just that the frequency of that light source is different. And so in both cases, you put something that's in front of it. If you look through a pane of glass, you can get the light that actually goes straight through it. If you put it as a sheet of plastic, it gradually, you can get to materials that change the opacity, and so it becomes opaque at one frequency and gives a color cast. And so you get light colored gels that you put in front of lights for cinema or for theatre. And so these are actually filtering specific frequencies. If you think of the radome material, it's again a filter, except that in this case, it doesn't produce something which you see as a color cast. It actually just attenuates all of the light that you were actually trying to transmit through it. So you've got a clear, as far as the Ku band radar is concerned, clear sort of radome in front of it, but you then use a completely different frequency and it then no longer appears clear. It appears as if it's an opaque surface. I think that's hopefully sort of what you were asking about.
Yeah, okay. We'll have to move on because time presses. There's one from Nick J. Have you considered combining both optical and radar-based images for greater information? Or are they, this is me saying, are they actually too disparate? Can you get useful cross information from them?
You can get different information from both. Some of the time you will see the same information. At other times, though, you will be looking at different aspects. I think trying to use them as a combined image doesn't necessarily mean that you're actually getting more information, but using the information that you can glean from both certainly could have advantages.
Okay, one from Robin. Did you do any trials over water? Does sea state present problems with clutter obscuring objects?
The main challenge with the sea the collection times for the imagery that we were collecting, because we were just in a standard turboprop aircraft, to fly our kilometre or 2 kilometres that we were collecting as apertures, or longer in some cases. I mean, we got some that took minutes to actually collect, and sort of based on the standoff ranges we were operating. And so the sea surface is actually changing quite significantly over the period that we're collecting. And this is where satellites have the advantage that they are moving incredibly quickly, and so therefore they cover their apertures very quickly. Because we were in an airborne sort of platform, we were having to fly slower, and therefore the sea state would be a limiting factor if you were trying to image from an airborne system and get to these fine resolutions. I think you've either got to trade off and work at coarser resolution, or go to higher frequency, or travel faster.
Okay. This next one you've partly answered, I think, already, from Philip Oakley. What aperture stroke standoff range ratio was used in most of the images that you got?
Typically, we're over a kilometre in the actual aperture. I think it's the actual ratio for the images to produce 5 centimetre resolution. You're needing about 6 degrees of integration. So you can probably plug numbers into that, and that will tell you sort of what apertures and what ranges. But we were certainly forming images which were kilometres in length for the aperture.
Right. Next question from Bill. Have you had any access to quantum processing? If so, what improvement would it give in imaging?
I've not been directly involved in quantum processing, and the honest answer is, at the moment, I don't know.
Well, perhaps
I'm not sure that I'm in a position to actually talk authoritatively on that.
Since I've given a talk on it, perhaps I could say my personal view is it might do in the future, but not yet. And quantum processing will really take off when it becomes room temperature, which it isn't really at the moment. It's a difficult technology, but it may well come. If you've got a desktop quantum computer, then yes, the answer, it could well give some improvements. Next one is an anonymous attendee. Could this radar be used from the ground, and at what range could it operate out to?
You can certainly use radars at this frequency from the ground to look up. If you look up a radar called TIRA, T-I-R-A, you'll find that this is an imaging radar that's ground-based. Has, I think, I can't remember if it's used for imaging satellites, and I think it's got tracking and imaging radars at 2 different frequencies. So certainly you could use a very high-powered radar to look at satellites, and that's something that is done.
Okay.
Actually, using this particular radar, I think the power is too small to start looking at those ranges. It was defined or designed to be high resolution imaging of the ground rather than imaging objects at a long distance.
Okay. Can the next one question from Michael Beasley? Can one minimize the radar sufficiently for viable use on smaller UAVs, also taking into account power requirements?
There are certainly a number of things that can be done. We've reused a form factor that is common with optical sensors. So therefore, actually finding holes in aircraft that you can bolt it into becomes easier if you fit the same form factor as an optical sensor that may have already been fitted to that aircraft. But by repackaging, yes, you can make size and weight savings. Processing power has gone up significantly, and therefore the power consumption for the processing part of it could drop by just keep on moving forward in generation of processors. As to how small you can make it, certainly some of the smaller UAVs, there are some of the small drones, the larger end of those that have been used experimentally for forming radar images like this.
Okay. The next question again, well, a couple of questions I think have probably been answered so already by you. Sterling Essex asks, can the multi-view processing be done in real time, or are these images post-processed? I feel you've answered that already, or do you want to add anything to it, Malcolm?
I mean, with the post-processing that we've developed, we've gone out of our way to optimize it so it'll take advantage of GPUs and multi-core processors. So it does work pretty quickly, but it depends on how large and how many images you're putting together. So it's not real time to actually collect all of these images, and it's probably of similar orders of length of time that you would actually take to combine them again.
Okay. Anonymous attendee, again, how does multi-look cope with continuously moving objects such as sea surface? I think you've almost answered that. Can the advantages of multi-look be achieved for this? I feel you've answered that. Do you want to add anything?
You would tend to average out so that the things that are consistently moving, you would start to be able to detect more easily, and the things that are randomly moving would actually get harder to see, and so you'd average it out. But I think for the sea surface, the answer is you have to travel faster or work at coarser resolutions in order to actually get imagery of the sea surface for that use.
Right. Paul Davis asks, if you went to higher frequencies in an attempt to get finer resolution, would there not be practical problems like detector timing resolution and other accuracy limitations?
I don't think that the challenge there is the timing, because if you go to higher frequencies, you don't necessarily generate and sample at the higher frequencies. You can use down converters and sample at an intermediate frequency or down at baseband. And so therefore you can shift the problem there. You can also, if you haven't got the bandwidth to actually sample the whole of your signal, then you can use techniques such as stretch compression, which is one of the techniques we used, to mean that you can work with a smaller bandwidth than you're actually transmitting in the receiver. And so therefore there are techniques to get around that. Moving up to higher frequency bands, I think that the challenge would be getting components and power.
Right. There's a comment from John. He's partially solved his problem with getting his image right, so we'll move on. Good luck to you, John. Philip Oakley, how near thermal photon noise floor is the imaging? Are you worried, in other words, by thermal noise in your system?
Thermal noise is something which just affects the range at which you can operate. And so therefore it's going to be present in the background of the image. The further you go away from the scene that you're trying to image, the more apparent it will become, because your signal level will drop and the thermal noise will stay the same. We've made no attempts to cool the receiver or to do anything. So it's probably operating a little bit above room temperature. By the time you've stuck a microwave power module and all of the other equipment in there in close proximity, you're probably working slightly above that.
Okay, and next question partly answered already. What are the legal limits for transmitting for this kind of radar? I assume it matters on the power level being transmitted, but are there some legal restrictions which you have? So you'd have to operate in a lab rather than taking it outside. Do you need a license?
You have to get a transmit license to operate a radar, and so therefore, whether you're working at the lower frequencies, X-band has up to about 2 gigahertz, where radio location, so radar, is either a primary or a secondary user. Similar at KU band, you've got around about 2 gigahertz. There's actually Ofcom, and in various other countries there are similar regulatory authorities that allocate these bands, and many of them are multinational, so that you have the same bands available in multiple countries. But it limits the resolution that you could achieve at the lower frequencies. For Ka band, we were able to transmit over 3 gigahertz and get a transmit license for operating. And so therefore, it's less of a limitation at these higher frequencies. If you go further up in frequency, it then becomes easier to achieve these relative bandwidths. And it also is easier to get a transmit license for those.
Okay. Simon asks, do you see any benefits in moving to even higher frequencies, and what might be considered for this in the future?
There are probably arguments for moving up in frequency, particularly for short range operation. If you're doing something which is providing something such as scanners at airports, then going up in frequency makes a lot of sense. If you are trying to minimize the size of something and work on a vehicle, and so you use radar for that application, then you don't need long distance. You don't need to be able to see kilometers in front of you. You only need to see sort of a few hundred meters to cover the objects that are actually going to affect you. And so for these applications, going up in frequency makes a lot of sense. For long range surveillance, then it's more challenging because you've got to get more power and cope with more absorption to work at even higher frequencies. But there are applications where it will still be efficient to do so. So if you want to work relatively short range, say helicopter landing, trying to actually get a quick view of what the scene is, even when you've got a brownout or dust being blown up, then there may be application for going up in frequency there.
Okay, well, I'm afraid we're running out of time. With just one more question, and then we must start signing off. And this is basically, could you use, from Ian Simpson, could you use SAR to enhance the resolution of millimeter wave imaging for security? In some way, multiple receivers, etc. Could you scan multiple targets as well?
Well, synthetic aperture radar is taking one antenna and physically moving it, so it doesn't really naturally sort of match up to that particular application. But having it as, say, for airport security, where you actually move the sensor either vertically or horizontally at some point where people have to funnel through turnstiles or something like that, could possibly be seen as something that could be done.
Okay, well, at this point, Malcolm, I think we must draw it to a close. It's been a fascinating talk, and on behalf of the IET and all, also obviously the interesting people, questions which have come in, and I've never seen so many questions before. Thank you very much. It's really been very good, and I think really it's a matter of saying good night. We used to say safe journey home, but I think most people will be taking a journey to the drink cabinets at the moment, and certainly you deserve to do the same. So thank you very, very much. And just another comment's come up. Thank you for a very excellent lecture. So the comments have been coming in that way. Now, I think that's one final point. Just a reminder to David, the CPD he's from David, I should say. CPD has now been come up from that. So good night, everybody, and I think we'll just wait for a few moments and then sign off. So if you like to bow out, Malcolm, then thank you very much.